Stanford University.
Welcome to the seminar on People, Computers, and Design. I'm Terry Winograd, and next week our speaker is going to be Vladlen Colton, who's on the faculty here in our department in computer science and is doing a project on virtual worlds, sort of looking at both the technical side and the interaction side to make them feel more natural, to making a more appropriate, inviting place for social interaction. So next week is virtual worlds. Today is the opposite of virtual worlds in a way. We have Bjoern Hartmann, who is a PhD student in our group, in the HCI group here, who's just completing his work. He'll be leaving us sometime later this year, unfortunately. He has brought in his work, a real emphasis on the physical world. So his focus conceptually is on prototyping, but what he's really been interested in a number of ways over his career here is how do you prototype things that have both a computational side and a physical embodiment that you're prototyping as well that you care about. He's developed a series of tools and approaches to this, as well as doing a lot of field work, actually interviewing, talking to people who prototype different kind of things, understanding how you do that. One side comment, I was thinking last week we had Bobby Fishkin, who in addition to his computer work was a playwright, and we have Bjoern, who in addition to his computer work is a musician. Before he started here, he actually had his own record label and did music in Europe. So I think there's something about coming from the arts that actually is a great advantage in HCI. So today we have Bjoern.
All right, Terry, thank you for that introduction. I just make sure I'm all set up here. Great, so today, over the next hour, I want to talk to you about my dissertation research, which focuses on proposing new prototyping tools that foster both iteration and exploration during the design of novel user interfaces. And the starting point for my work is the observation shared by both people who practice design and people who study people who practice design that prototypes are central to good design in any domain. And that prototyping really is the pivotal activity that structures innovation, collaboration, and creativity in design. And it doesn't matter whether you're designing toothbrushes or medical devices or user interfaces. Prototypes embody design hypotheses and enable designers to test those hypotheses. And the goal in prototyping is not the artifact. Prototypes are valuable because they enable exploration and iteration around concrete artifacts. So you build some prototypes, evaluate them, and use what you learn to drive the next design. Now, any sufficiently complex problem always has a space of possible solutions. And to map that space, designers frequently generate multiple solutions to a problem simultaneously to then select the most desirable candidates of that set. For example, Paul Bradley at IDEO rapidly created about 80 different models to explore different possible shapes for an early version of the Microsoft mouse. Design through iteration, on the other hand, acknowledges that finding a fit between a problem and a design solution can only really be achieved through repeated testing and improvement. Take this example. This is from the ongoing public redesign of Drupal.org, which is the site for a popular open source content management system. Designer Mark Bouchard here publishes his iterations, his prototypes for the new homepage online, and then elicits feedback from the existing user community. And around every week or so, based on that feedback cycle, he comes up with a new iteration that improves both content, information architecture, and visual design. So even though exploration and iteration are core activities in design, it's somewhat surprising that neither are particularly well supported in today's user interface design tools. The focus of today's design tools for user interfaces is getting a single complete product built. And of course that part is important, but it's not the entire story during prototyping. Here's an example quote of shortcomings of current tools. So Brad Myers at CMU recently published a survey of 259 interaction designers. And one of his findings was that designers frequently wanted to have multiple designs side by side. So this is that exploration of alternatives. However, there's no built-in way in today's tools to actually do that. Well, why do we actually care about that? After all, products do make it to market. Some websites are also being published. Well, we know from studies of designers that designers tend to hang on to initial solutions for quite a while. Now, if your design tools don't foster exploration, then you're going to make those initial decisions with insufficient knowledge of the larger space of designs. If your design tools don't foster iteration, well, you may never elicit feedback early on, or if you do elicit that feedback, you may not have a good way to act on it, so that gained knowledge may be lost or not acted on. And finally, if your tools don't support the processes that you want, then designers are simply going to waste their resources and time in working around the wrong abstractions in the tools. The result of that, you'll uncover problems too late when it's too costly to fix them. You end up with poor solutions and failed products. All right. So in my dissertation research, I tackled this lack of support for iteration and exploration in design tools in 3 areas. First, there are rapid authoring techniques. Think of these as the minimum baseline. If you can't build a prototype fast enough, you're not going to iterate and you're not going to explore. And specifically for the domain of off-the-desktop interfaces that have physical embodiments, tools are still lacking. So I'm going to show you a project that introduces visual and demonstration-based authoring of hardware and software in concert. Now, to support iteration, I'm going to argue that we want to capture and manage feedback from testing of prototypes directly into the design tool itself. I'm going to show you techniques for correlating state information, a software model of a prototype, together with video of a test of that prototype. Finally, to support exploration, I'll argue that we should really be able to create multiple alternative user interfaces in parallel in a design tool. And I'm going to show you techniques for parallel authoring and runtime tuning that seek to achieve that. All right, so let's get started with the first area, rapid authoring techniques for sensor-based interactions. Actually, before I tell you what I've done, let's take a look back at some really successful projects in the past. And I would argue that really HyperCard was the first majorly successful rapid prototyping environment for graphical user interfaces. So successful, in fact, that the game Myst, one of the big highlights of the 1990s, was actually entirely prototyped, the entire narrative flow, in a HyperCard stack. Now, HyperCard and other projects such as Silk or Denim assume desktop-centric development. That means you know what inputs and outputs are available. You assume that there's one screen and that input is going to come from keyboard, mouse, and maybe stylus. So what if we take that assumption away? Well, there are also some research projects on rapid authoring of physical user interfaces. Projects such as Saul Greenberg's Fidgets enabled programmers, people who are happily writing things like callback functions and event handlers, to extend their current knowledge into the realm of controlling sensing and actuation. What these projects do not offer is that same kind of low-threshold visual authoring and direct manipulation that graphical user interface designers became used to from applications like HyperCard and Flash. All right. To kind of bridge that gap, we developed Dtools, which is a visual storyboard-based authoring environment. And it's the first toolkit really to unite both the design of what a physical device can sense and output. So what's the form factor, what kind of I/O affordances exist, and the dynamic behavior. So what's the logic running behind it in the same tool? Let me start maybe with an example to make clear what level of fidelity of prototyping Dtools targets. Take the mobile text entry problem. So if you don't have a touch screen and you have less buttons than letters, how are you going to type text? Well, researchers at the University of Washington a couple of years ago proposed a new entry method using a combination of buttons and tilt data from a built-in accelerometer. So how well would such an input technique work? This is precisely the kind of questions that a Dtools prototype can answer. Right, so here's our rebuilt prototype of tilt-based text entry. It's slightly larger than a wristwatch, which is just because of the size of displays that were available. But with the same input, so there's 2-axis tilting and a small number of buttons underneath the fingers. And it takes about 1 afternoon of work to get a functioning prototype like this built with Dtools. Now, in this video, you'll see we were able to prototype the published technique of first using buttons, followed by tilt to type letters. Now, more importantly, though, Dtools was rapid enough so that we could also ask what would happen if we reverse the control structure, if you first tilt and then use buttons to select a letter. Now, it turned out, because tilting is more error-prone, the second technique actually outperformed the method that was published at a conference. So having a rapid enough tool supported this serendipitous discovery of a better design solution. How would one author such a prototype with Dtools? Well, you start by plugging in physical components, such as sensors, into the Dtools hardware platform. As you do that, virtual counterparts appear in the authoring environment on the PC. Interactions are authored by creating visual states, which encapsulate output, and linking them through transitions, which get triggered by input events. This diagram itself now is the software model and can be tried out at any time. However, if you don't have hardware present, there's also the option of simulating hardware. Oops. Sorry. All right. So what you saw in that short video clip was there are basically 2 complementary editors. The first is that device designer on the left. And this is where the blueprint of the device is being laid out. What inputs and outputs exist? And I'm arguing that having such a representation reduces the cognitive friction of switching back and forth between designing hardware and then authoring what that hardware should do on the computer. Now, in the video clip, you also saw a plug-and-play technique where you can plug in a smart component and a virtual counterpart appears. To make this interaction possible, we designed our own hardware platform where each individual component, each button, each LED is smart and has a small microcontroller attached to it. So when you plug it in, that microcontroller then can report an ID and the capabilities of that component back to the software. Designers define the prototype's behavior in the storyboard editor, where states encapsulate output and events trigger transition from one state to another. Well, while testing early versions of this interface, we landed at the following questions. Question: how can we help designers map continuous sensor data to these useful application events? It turns out that the most interesting sensors, such as accelerometers, phototransistors, or rangers, are also the most troublesome to work with because the real world is noisy and often nonlinear. So while a designer will definitely know how to perform the input they want to recognize, whether it is a Wii tennis or golf swing, symbolically specifying in code how that input should be recognized is a much harder problem. Now, a research question was, can we actually use the performance, the swinging of the virtual tennis racket or the golf club, to do the work of specifying the computation? Now, to people in the audience who may have an AI background, that may just sound like the standard machine learning problem, right? You collect an example set and then learn a right classifier from that. Well, yes, but the algorithms are only the back end. Even if you have good algorithms, you're not done. Because the real question is, from my perspective, what are the appropriate interaction techniques that make this kind of real-term learning from demonstration feasible for interaction designers? And our insight in this project was that it's possible to combine recognition, so the smarts of the algorithm, together with direct manipulation and information visualization to also leverage the smarts of the designer. Therefore, the most important related work is actually not in algorithms, but in new interfaces for programming by demonstration. So on the left side here, you see Crayons, which was the first program that let users draw directly on camera images in order to learn computer vision classifiers. So here, a user drew on the hand and said, recognize things like this, and then drew in a different color on the background to say, and I'm not looking for anything that looks like this, that looks like desk or keyboard. Another point of related work is FlexiGesture, a project from the MIT Media Lab, which is an electronic instrument that can learn how you want to play it. So users program initially which movements they want to trigger which different sample playbacks. All right, next, let me show you a video of how we believe that authoring by demonstration could work for interaction design. So, with this project called Exemplar, an interaction designer first hooks up a sensor, such as an accelerometer, and then demonstrates a sensor-based interaction, such as shaking the accelerometer. She then marks the signal region that corresponds to the demonstration. This is the definition of an example. She can then immediately test by performing that action again and get real-time feedback whether that was recognized or not. Now, what do you do if the recognition failed? Well, this is precisely the question where interaction design, the designing of real-time feedback and modification of those events comes into play. So, Exemplar here introduces two techniques. The first one is thresholding. So you define an example, and we just calculate the minimum and maximum values. Now, computationally, this is a rather trivial technique. However, it's a very powerful technique because it has a really straightforward visual interpretation. Right? I know what's going to happen because I can just trace whenever that signal graph dips into that region between my minimum and maximum thresholds. Now, in the real world, if you work with actual signals, simple thresholds actually don't get you very far because you get lots of oscillation and just general noise in your signal. So what engineers usually do is add a layer of complexity, such as double thresholding or defining minimum durations of events, so you don't get rapid on-off fluttering. Now, these things also have direct visual representations, and we incorporated those into Exemplar. So for example, you can just split thresholds to get hysteresis, or drag a timeout bar to define a minimum duration of your events. And as you modify the definition of your events, we always recalculate for the entire history of what has come in before how your new event would have been classified in the past. So you get visual feedback as well as the opportunity to do new testing through new demonstrations. Now, what about gestures? Performances that vary over time. Thresholds are not enough for those. Well, for more complicated patterns, Exemplar includes pattern recognition techniques. The idea here is still the same from a control point of view. You mark up a demonstration, perform the action again to test it, and you have a thresholding slider to control how permissive or how general your event detection is. However, under the hood now, we completely swapped the algorithm out. For pattern recognition, we employ dynamic time warping, or DTW. This is an algorithm that was introduced in the late 70s in the realm of speech recognition. It uses a dynamic programming approach for sequence comparison. That is, given some example sequence, a demonstration signal, how much do I have to distort the current incoming signal in both space and time to match my demonstration? For those of you interested in algorithms, one point to note is dynamic time warp is quadratic in both time and space, which sounds like a headache at first, but it actually is not bad at all, partially because n is here the number of samples that we take of a signal, is small. It's generally sufficient to sample human motion at around 100 hertz, and any demonstrations, any gestures for interaction are generally less than a second long. So it's not a problem at all, even with a reasonably complex algorithm, to run, let's say, 8 channels of recognition in parallel. All right. So I showed you both visual authoring and demonstration-based definition of sensor events. The next question is, how do we know that these are any good? So how should you evaluate design tool research? Turns out the answer is a little bit more complex than the nice model we have for new interaction techniques in HCI, where you take an existing technique, improve it, and then do an A-B comparison in a controlled experiment. Well, if you enable a new group of target users to engage in the practice that they couldn't engage in before, you lack a natural B comparison. So what can you do instead? Well, I would argue that your best shot is to employ a triangulation of different evaluation methods. And we've done that for the systems shown here. So for example, to understand the trade-offs of Dtools as a visual programming language, we carried out an expert inspection according to the cognitive dimensions of notation framework. So this is a survey developed by cognitive scientists. It just asks a sequence of questions about any authoring environment. To determine the threshold and utility for novices, we conduct first use studies in our laboratory. These give you really fine-grained detailed data because you can videotape everything and afterwards analyze those videotapes. However, they have some important limitations. Namely, you're conflating the learning curve of first learning a new tool with the actual usability and utility of that tool. And secondly, the tasks that you pick for people to perform in the laboratory, well, it's not clear that these tasks are actually indicative of real-world design problems. So, after first use laboratory studies, we then also try to deploy our tools in the wild through class and industry deployments. Here you have much less control of what people are doing, and you get much less data back. But you have a guaranteed measure of ecological validity. That means your tools are actually applied to problems that matter to users. So here's a screenshot, here's a photograph, rather, from our first use study with Dtools. Here, we asked participants to solve first some close-ended warm-up design task and then an exploratory design task to build an MP3 player prototype. In a follow-up lab study, we also asked participants to create new sensor-based controls for existing games. And here are 3 examples. So one participant created a makeshift booth. We're hitting walls and stomping on the floor, navigated a spaceship. Another used an accelerometer mounted on a bike helmet to detect ducking down. And this is probably my favorite. A third participant used a handheld mini joystick and a bend sensor taped to the table to aim and shoot rubber bands. So other than engaging video clips, what do we get from these lab studies? Well, this set of 2 studies showed that the combination of plug-and-play hardware, visual authoring, and demonstration-based event definition lowered the threshold sufficiently so that even novices who had no prior exposure to working in this physical interaction design space could get up and running quickly. So we can tell that through just measuring task completion times. These are for that MP3 player prototype MP3 player example that I showed.
What are the units? Oh, minutes.
In minutes. Now, the other thing that we can tell is actually if we break down, if we just do video analysis, what did people in their 30, 40 minutes spend their time doing? Well, we're actually approaching parity between the design of the behavior in software and the design of just the physical form factor cutting out foam core, gluing sensors in. If we're actually approaching the same time to work in software that we do in foam core, I would count that as a success, as foam core is definitely one of the preferred methods for physical design really early on because it's so rapid to work with. As I mentioned before, after lab studies, we then also deployed our tools to interaction design students, actually here in CS 247 for 2 years at Stanford. And what I want to highlight here is actually an example of really successful industry collaboration. So Leapfrog, the electronic toy company, came to us and was interested in using Dtools in their advanced concepts group for prototyping. And in exchange for me going into Leapfrog and just doing a series of workshops to teach the system, they then offered to manufacture a whole set of hardware interfaces for us, which we could distribute to students. All right, to wrap up this part of the talk, what are the important ideas in this first section? Well, Dtools and its add-on, Exemplar, the demonstration-based system, successfully enabled non-programmers to prototype novel sensor-based user interfaces and do that rapidly. And the two important techniques that enable that are virtual modeling of the physical device right next to defining what that device should do in software. And second, the programming by demonstration for sensor events, so that you could define much more complex interactions than you could do through simple conditionals that designers may be comfortable in writing in procedural code. And finally, the point that design tool research, just evaluating it, requires a triangulation of different methods. All right. Let's move on to the second of our 3 chunks, supporting iteration directly in design tools. So before I set out to write any code for any of these projects, as Terry mentioned, I engaged in contextual inquiry, so calling up industrial design companies in the Bay Area and trying to get to know their product teams and the status quo of what they're using. Now, one of the results of that inquiry was that user tests, even of really informal prototypes, are frequently video recorded because you want to have something to refer to later on. However, that video material ends up rarely being used afterwards because it's so expensive in terms of the designer's time to go through hours of video and find the right section. So the typical use case is I have 2 or 3 hours of user test data, and I just want to find the 2 5-second snippets that I want to share with my team of the major breakdown or the major success. Well, we had the insights that it's actually possible to integrate the design, test, and the analysis of a prototype within a single tool, so that later on we can then leverage a correlation between the software model, what the prototype does, and the collected test data, someone using that prototype. So I'm going to show you, we augmented Dtools, the design environment, with both test and analysis modes. And we're going to show you test mode first. In test mode, Dtools just records a video and logs the user's interaction with the physical prototype that was built in Dtools before. So here a camera is pointed at the tester, and live video from that camera is recorded and annotated in real time, both with what state the user was in and what events were generated on the prototype. Now we can supplement that then also by the experimenter pushing a button that says, a special event that just says, look at this later. All right. After a test session is completed, designers can then leverage that tight synchronization between the software model, the video, and all of the state and event trace data. So in analyze mode, it suggests itself to use a dual monitor setup where you can see the software model of the prototype on one screen and the recorded video on a second screen. Now, what do you actually gain by looking at those two side by side and having the structuring event data? Well, First, you can now access the state chart through the video. So as I play back video, and as the video head moves through time, we can highlight in the software model what state the prototype was in at any point in the video. And not only that, we can also visualize what state someone came from and where they're going next. So kind of a look forward, a look ahead in time. Secondly, you can now go the other direction, and you can access the video through the state chart. That means you can now just click on any state, and that click essentially performs the query, show me only those video segments in the entire recorded video where the user was in that state. So it's a really rapid query mechanism. And you can not only do that in software, you can also extend that in hardware. So if I want to see the video segments where the user moved the volume slider on the right-hand side of the device, well, why don't I just move the volume slider and let that be the query? All right, so once you've analyzed that video data, that probably suggests a whole number of changes to do for the next iteration. Well, design's a team sport, and it's rarely done alone. So quite possibly, the person who reviews and analyzes that video is not the person who performs the actual changes in the prototype itself. Which brings up the question, how may we be able to support designers in the act of annotating and revising their prototypes? Well, maybe we can get inspiration from some other domains. So, in the design of purely visual things like graphic design, or this is a still from Pixar in movie production, what we find are tools for rapid graphic annotation. So here, a producer would draw on top of the daily renderings at Pixar to suggest that a movement in a frame really should be further to the left. In programming, on the other hand, so where we define behavior, and remember, interaction design is that combination of defining both the appearance and the behavior of something. We have a history of more formal revision tools that compare different versions of documents and easily give you options to merge, accept, or reject changes. So how can we combine these two kind of histories of both free-form annotation and more formal semantic revision actions for interaction design? Well, I actually don't have the answer, but I started to look into this recently with some summer interns. So we started to extend Dtools to allow you to both do any free-form annotation and to also specify, just as in Word, where you can track changes. You can track changes by adding, deleting, or modifying behavior. And this work is very much in progress, so I just wanted to give you a quick preview. Now, related work for supporting iteration, well, there isn't all that much. There's a smaller body of work from the mid-90s that has looked at how we can speed up the review of user test data of a piece of software. So, for example, iObserve introduced a regular expression query language for video. But none of these systems were actually integrated back into the design tool, so you never really know where these events came from or what state a program was in when something happened. And then on the other hand, there's Scott Klemmer's Suede system, which enabled you to do design, test, and analysis, but of speech user interfaces. So here, the kind of basic building blocks are just very different. Namely, everything is done in audio, so there is actually no need to develop video techniques. All right, so what was important about this segment about supporting iteration in design tools? Well, hopefully I've shown that integrating analysis of test data into a design tool can radically shorten the time that's right now required to work with user test videos. This integration is enabled by having a high-level visual representation of the software model of that prototype. This does not transfer one-to-one to prototypes that you coded up in C++, because there's no good correlation to exploit between a point in video and a line of code that was executed at that point in time. There's simply too much procedural code that runs by too quickly for that to make much sense. So you need some kind of higher level abstract representation. And I suggest that using a state-based approach or a storyboard-based approach is actually a useful abstraction for that. And finally, design is a team sport, so new revision tools are needed to record insight and suggested changes between different iterations. All right, let's move on to the third section of this talk. The third section here is about exploration. How can we design multiple interface alternatives in parallel? Well, maybe once again, we can start by looking at what people have done in other domains. So, both in 3D rendering and in image processing, research systems exist that have realized and exploited the importance of exploration and build tools around those. For example, design galleries addresses the problem of how to find suitable parameter combinations for 3D renderings, where you may have things like particle systems that themselves have a third-dimensional space of parameters that you need to set. And regenerating every image may actually take a while. So what design galleries did was say, hey, you give us a description of the parametric design space, and we'll just generate automatically overnight examples everywhere in that space. And then the next morning when you come into the office, you can have this structured browser that shows you all of these different points in parallel. Oops. Spreadsheets, as seen on the right, also inherently support parallel exploration, because you can put one experiment spatially next to the other. And Mark Lavoie has used that feature to program spreadsheets for image manipulation, where you can have both images and different image processing operations occupying the cells of your spreadsheet. Now, can we take either this automatic generation of alternatives or this kind of juxtaposition in a spreadsheet format and apply it one-to-one to interaction design? Well, unfortunately, not quite. And one of the reasons is that research projects such as Dtools notwithstanding, that in practice, interaction designers today are forced to write some amount of code. Whether that is ActionScript in Adobe Flash, whether it's HTML and JavaScript in Dreamweaver, or whether it is Java in Arduino and processing, two environments very popular with digital artists these days. Now, once you work in code, you have a problem of working with two representations. There's the code where you make the changes, and then the running program where you observe those changes later on. So how do interaction designers deal with this today? How, even in the lack of tool support, do interaction designers who write code, which is not all of them, but a sizable subset, try to kind of retrofit exploration into their design tools? Well, we conducted a number of interviews and asked our participants to bring in the source code of recent projects they had worked on. And from that exercise, we derived 3 requirements. The first one is that arriving at a satisfying user experience often involves tweaking the dials of an application. So you have a code base that kind of stays the same, but you keep changing the parameters, maybe how fast something animates, and other parameters like that, to to hone in on your imagined user experience. Second, to compare different behaviors, it may also be necessary to change the code itself. So here's an example from our inquiry where our participant wrote this function code that actually has two alternative ways of computing values in the same function body coexisting. And he would just comment one out, run the program, then switch the comments to the other lines and run the program again. And I believe that tools should support the creation and management of these different code alternatives automatically instead of this rather awkward technique. And then finally, management of code and data alternatives really has to work both the editing across both the editing and execution environments. So expert programmers already do that today. As part of testing an application, at some point, they will write an extra window that just has sliders to tweak the behavior of the application while it's running. Now, that code actually is not part of the final application at all. Right? It's purely code written for the purpose of exploration. And I believe tools should be able to construct those control interfaces automatically. Now, to investigate how these three requirements may be addressed, we constructed Juxtapose, which is an experimental tool for working with multiple design alternatives in parallel. The basic idea here is that we have an augmented editor, so at the source level, we keep track of alternatives in different document tabs. These alternatives can then be executed in parallel, which allows for rapid comparison between them. And finally, Juxtapose also adds automatic generation of control interfaces to rapidly tune parameters of a running application. All right, let's start with the editing part. To make working with multiple code alternatives feasible, well, that kind of sounds like a headache for the programmer, right? So to actually make that feasible, your editing environment has to give you some support. Namely, it has to offer techniques for manipulating content across different alternatives. And it also has to make those differences visually apparent. So you can reason about what stays the same and what's different between your alternatives. So in the Juxtapose editor, alternatives are accessible through document tabs. And edits you can make to the document you're viewing can be either global, which means even though you're in one tab, whatever you change gets propagated to all other tabs. Or they can be local by toggling a linked edit mode. To visualize what's the same and what's changed, we then simply highlight text entered in unlinked edit mode. So this is the text that's only in this particular alternative in one background color, while leaving all the other text with a white background color that's shared. All right. How would you actually make this editor work? Well, the underlying problem here is cursor correspondence, which means if I'm in alternative A and I enter a change at position N, what are the equivalent positions in my other alternatives where that change should be inserted, given that those other alternatives may already have a different document structure? Well, the straightforward solution is that you basically want to use the longest common subsequence algorithm, diff, and the naive answer would be you just run that after every keystroke over all alternatives. There's a little bit of a longer answer of how to make that efficient and maybe only run an expensive algorithm during idle times, but I'll skip that, the explanation of that. Okay, so how would a designer use parallel editing for exploration? I was looking for the simplest possible example that would make that point. And I came across this WIST paper from 2007, Rethinking the Progress Bar, which was a neat paper that demonstrated how different progress curves, so how you go from 0 to 100% progress, affect the perception of how fast something is progressing. So even if it takes the same time, if you take a ease-in curve versus a linear curve, it actually feels different to you. Well, this is a prime example of alternative exploration, right? In each case, the application you're running is only show me a progress bar. and what you're changing, so all of that machinery of how to put that on screens stays the same. And all of your changing between the different alternatives is just that function mapping. So here's how exploration of that would look like in Juxtapose. I defined 4 source alternatives. In each, I only changed 2 lines of code. One just to give you a text label of what the condition is, and the other to change the mapping function. Juxtapose now executes all 4 alternatives side by side, so I can quickly review them sequentially. Now, sometimes it may also be advantageous to view things in parallel, which brings up the question, how do you interact with multiple programs in parallel? In the general case, this is a hard problem. There may not be a solution. However, that doesn't mean that you shouldn't build any tool support for that. So in the case where the visual layout of your application, of your alternatives is the same, you can actually do parallel input, where you intercept input, such as the mouse, in the active alternative, and then inject a fake or ghost mouse cursor into all other alternatives. This now gives you the opportunity to interact with multiple running programs simultaneously. The other requirement that I mentioned was that interaction designers want to be able to explore parameter spaces. So Juxtapose can automatically generate control interfaces from variable definitions in the user's program. When these control widgets are then manipulated, we'll change the variable value in the running program. When might this be useful? Well, here's another example from the WIST conference 1 year later. Patrick Botish's phosphor system introduced a way to have visual afterglows that show you when a widget was manipulated and what its prior state was. The idea behind a system such like that would be it would be able to explain your interaction when multiple people are looking at the screen, or in a remote collaboration scenario when you may have multiple cursors. Now, the parameters of concern in terms of user experience here may be the timing characteristics and the color balance of that afterglow. So how long should it stay on screen? How fast should it fade? Does it look better in the green direction or in the red direction? So here I re-implemented phosphor in ActionScript in Flash. And when we run phosphor within Juxtapose, you see on the right-hand side that automatically generated control interface from variables in the program. I can now, while the program is running, adjust these variables to experiment with different visual effects. Now, once I've found a set of useful parameters, that set of parameters can be saved into a snapshot that you can recall later. So here's one more level of rapid A/B comparison for exploration. All right, so how would you actually make this technique work to automatically generate control interfaces of an arbitrary program that you didn't know because it was the designer who wrote the code, right? Not the author of the tool. Well, fundamentally, you just need some bidirectional data exchange between the user's program and your own runtime environment that kind of wraps around it. So to achieve that, when the user compiles their program, we just add on a small library component. When the application starts up, that library then uses language reflection to look into the user's application and extract names, types, and initial values for all global variables. These are then sent through a remote procedure call across process boundaries into the Juxtapose runtime interface. From that information, we can then generate that control interface. Then later on, if any of the widgets in that control interface are manipulated, we can send another remote procedure call back into the user's program, specifically into our library, which can then update the variable on the fly. All right. Popping back up from implementation strategies to higher questions of why would you actually want tuning? Well, we asked ourselves the question, when is this type of tuning most useful? So we once again had a controlled lab study where we created a close-ended task that asked people, given code that procedurally draws the tree given above, change the parameters in the code to produce the 4 trees given below. Now, this is clearly pretty far removed from something you would actually do in design practice, right? But because it has that really concrete goal, it allows for nice measurement of performance. So, unsurprisingly, if you give people sliders to change parameters, that's a lot faster than if you have to re-edit code and recompile and run, right? But direct manipulation is good. We kind of knew that. The more interesting question is, when does it provide benefits? Can we give a more detailed answer? And yes, we can. So if we dig deeper and look at the task completion times people with and without Juxtapose had for different trees, well, it actually only turned out to be a significant difference for these 2 trees. Why was that? Well, it turned out that for trees 1 and 2, people did pretty well reasoning about how to change parameters and how to approach that goal analytically, and then would just take a guess, try it out, refine their guess. For these 2 trees, because of interdependencies of parameters, people did pretty poorly. They could approximate the tree shape, but then they couldn't reason about it anymore, and it turned into a multidimensional trial and error exercise. And it's precisely in this trial and error phase, when reasoning about the problem can't get you any closer to the solution, when tuning was the most beneficial. So if the value is really in multidimensional exploration, then it actually turns out that the mouse is a pretty poor control interface, right? Because you can only ever manipulate one parameter at a time. So recognizing that, we then extended Juxtapose to support the use of an external controller, such as this meaty slider board. Using such a controller has 3 benefits. First, you get multidimensional variation. Second, your eyes are still free. You can just rest your fingers on the sliders, and your eyes are left free to focus on the running application, not on whether your mouse cursor hit the right control slider. And third, by using an external controller, this leaves you free to tune interactions that actually depend on mouse input, such as how do I want to link the mouse scroll rate to zooming in a map? Right? That requires an awkward switching back and forth if you use the mouse both to test and then to control what you're testing. The next question we asked ourselves was, well, okay, so we've identified some principles by which parallel exploration is feasible for desktop applications. Do any of these hold if we go beyond graphical user interfaces and back into the realm of physical user interfaces or maybe mobile applications? Well, mobile phones are commodity hardware, and mobile developers already routinely test on a whole array of different devices. So that gave us the idea to extend Juxtapose to leverage these device collections by executing different alternatives on different phones. Your phone, at least currently, is not powerful enough to rapidly switch between different alternatives on the same device. But if the devices are cheap, let's just use many of them. So this now enables designers to rapidly switch between alternatives by putting one phone down and picking another one up. Another very nice side benefit is that tuning now allows the designers to use their PC, where there's lots of screen real estate, to change the behavior of a program that's running somewhere else on a cell phone. Under the hood, things here are quite similar to the desktop implementation, with the exception that because your programs are now running on physically separate processors, you have to replace all that inter-process communication with socket communication. Now, to take it one step further, we looked at embedded microcontrollers, so things like the Dtools hardware interface. So these are the tools of choice for working with sensors and actuators. We specifically looked at the Arduino platform, which is rapidly becoming the kind of platform of choice for teaching interaction design and for artists. So building custom hardware is resource intensive compared to programming, right? So unlike for mobile phones, designers are actually less likely to build multiple physical prototypes right away. And if you look at current practice in places such as the Media Lab, you'll often find lots of different software versions kind of being shoehorned together into the same hardware platform and then somehow being switched with either software or hardware switches. Now, languages that run on such little embedded platforms, in our case, there was an 8-bit RISC processor with 16 kilobytes of memory, don't usually allow for nice features such as reflection, which we used to make tuning possible in the first place, because we had to, at runtime, get information about all the variables. So, how might one implement variable tuning in a language without reflection? Well, it's actually possible by adding a pre-processing step to compilation. So before we compile the user's program, we just parse the code, extract all global variable definitions, and build a symbol table of name of variable, type, and the code that will translate into a runtime pointer. We then take that symbol table and emit it back into the user's source code along with some communication routines. And then that modified program, that is what gets compiled and sent to the microcontroller. At runtime, when a widget gets tuned, the user library can then look up the variable name in that symbol table and just adjust values through pointer dereferencing. So popping back up, what's different across these domains? And it turns out it's not really so much about the technical barriers. So we've shown that there are implementations that make the difference in software architecture relatively transparent, no matter whether you're on a desktop, on a small microcontroller, or a mobile phone. However, it's the different intrinsic modes of interaction and the costs of making changes to the physical form of the prototype that actually affect how alternatives can be executed and how users will interact with them. All right, summing up this part. What's important here? Well, a structured approach to alternatives can eliminate the cruft, the bad practices we currently find, and enable more exploration. Supporting this in tools really requires support across both the editor, where applications are authored, and the runtime environment where they are executed. And Juxtapose demonstrated 3 possible techniques, which is linked editing to manage the code alternatives, executing programs side by side with either sequential or parallel interaction, where that's possible, and auto-generating tuning interfaces by parsing source code. All right, summing up. We started with the following question. How can user interface design tools support exploration and iteration? And that question really came from looking at the practice of design in different domains. And the contributions fell in 3 different areas of my research. First, the baseline rapid authoring techniques. How can we just make sure that in domains off the desktop, prototyping can be as rapid as working with foam core in physical space or as working with applications like HyperCard on graphical user interfaces? To support iteration, I suggested that we want to capture and manage feedback directly within the design tool. And to support exploration, I suggested that we want editing environments that allow for parallel editing and execution. Just a final note, so the last system I showed you, Juxtapose, is fairly recent, so there's not that much information available about it yet. However, the other 2 tools, Dtools and Exemplar, are discussed in 2 O'Reilly books. One is Making Things Talk by Tom Igoe, which targets kind of do-it-yourself hobbyists and artists. And then more recently, just in the last couple of weeks, Dan Saffer's Designing Gestural User Interfaces also discusses these tools. And that's a book that's more aimed at professional designers in helping them think of how to get to the next interaction model after graphical user interfaces. And then something that I actually just happened upon recently that was unknown to me because the author actually never asked me for any input. there's a group in Germany that used Dtools and downloaded the project. It's open source, so you can just grab it from SourceForge, and extended it to capture timing of user tests, and wrote a paper and published a paper at Chi about it. All right, going forward, here are 3 questions I'm thinking about at the moment. So there are a couple of other things that suggest themselves that are straight extensions from the research I showed here. Right? For example, Juxtapose. I've only talked about handling alternatives for programmed interactions. Well, what do we do for these kind of hybrid environments that most people work in, like Flash, where you have both ActionScript and graphical elements on a stage? So it's kind of an open question how to extend these techniques for parallelism to more complicated authoring environments. However, in terms of different questions, the first one is, what would a textual programming language for prototyping look like? And what I'm trying to get at is that what characterizes prototyping is ambiguity and a lack of resolution in a lot of parts of the prototype being created, right? You're mostly asking specific questions about one part of your project with a prototype, and everything else is somewhat undefined or faked for the moment. Now, our programming languages are not very good at handling ambiguity or faking. So can we rethink what the primitives of a programming language are from the ground up to support ambiguity? The second question is, how might authoring environments support the process of design by example modification? And there are 2 motivations for that. The first is the observation that almost no programming these days happens from scratch, where you just fire up Visual Studio and start typing into an empty window. Much more common is programming by finding examples on Google, pasting them in, and modifying them to fit your specific requirement. On the other hand, going away from programmers and looking at designers, it's a frequent practice that really early on, to get inspiration for a new project, you surround yourself with as many possible inspirational examples that you can find from the widest possible variety of sources. And finally, there's more of a longer-term blue sky project. What will the interaction design studio of the future look like? What I've shown you so far were a number of tools for authoring post-GUI interfaces, but the tools themselves were all still graphical user interfaces. So possibly, with technologies such as interactive tables, finding more adoption, maybe we can actually change what the physical workspace looks like in which designers do their work. So here, this is once again just a little teaser from work I did with collaborators at Microsoft Research, where we looked at what happens during early conceptual design meetings. And what really struck me was this wild coexistence of both digital and physical artifacts. Right? There's the sketch I made in my Moleskine while I was writing the BART, next to the printed out schedule, next to the PowerPoint or PDF presentation, next to some video prototypes. So right now, these physical and digital artifacts kind of live side by side, mostly unaware of each other, with no good techniques to transition between the 2 worlds. I'll just leave you with a short video of what some interaction techniques could look like to help bridge that barrier. So if you have a smart table, you could maybe just bring your design notebook, and the table itself could help you make digital copies of any of your physical artifacts. Or if you have digital documents and want to annotate them, maybe you can do that on whiteboard tablets. Or another transition technique to go from digital to physical space, taking any digital source image and quickly using your interactive table as a light table to quickly create a physical trace, which you can now walk away with in your notebook. All right. Of course, the work I showed today was not my work product alone. So I've had a fantastic and also sizable set of collaborators over the last couple of years, both within Stanford and outside. I'd like to thank them and also the companies that either used our prototyping tools or were instrumental during the contextual inquiry to gather requirements for those tools. For more information, I invite you to look at any of my recent papers, which are all on my website. Thanks.
Questions?
Bjoern, great work, awesome work. About your evaluations of Dtools, I totally agree that it takes sort of triangulation, getting it out there, trying it out in different ways. What were some of the specific things you learned about its development while it was being developed, and sort of take-home points from the evaluations?
Yep. So one take-home point that took me a while to realize is that in tool research, so this may not be specific to Dtools, but it may apply more broadly to design tool research, that while we're focusing on the research question, for example, how can you introduce new rapid visual authoring techniques, etc., but to actually be able to get valid external data, not just closed lab studies, there may be a whole bunch of extra work that has to go in that has absolutely nothing to do with your research question, but that is vital to get any useful real-world data. So let me make this example concrete. When we first deployed Dtools to students in CS 247, the only way you could get graphic output was by just dragging simple JPEG or PNG images to states. And that was about the support for output. The reason I stopped there was I said, well, people know how to write GUI editors. I don't think I can improve, as part of this project, on the state of graphical user interface editors. Well, it turned out what I got as feedback was, this is great for letting us work with sensor data. Now can we also tie it to Flash? What was really behind that was, this solved the problem for us for sensors, but we can't make dynamic enough graphics with it. Right? So as part of that, to actually get better real-world user data, we then spend additional effort to actually add a graphical user interface editor within the design environment. So this was just work that had to be done, that was not research, but without it, you wouldn't be able to get any ecologically valid, externally valid, long-term deployment data. Yes?
I have a question about evaluation that's where the core cases are a little removed from your domain. But I'm thinking if the evaluation criteria that you truly care about are in some sense second order or not easily observed by watching a user interact for some brief time that can be pulled over, relatively transparent to a designer looking at them, things maybe like safety, maybe learnability, maybe effectiveness as a teaching tool. I wonder if you have any thoughts about what sort of proximal predictors of these distal events there might be and how that sort of thing might be supported or incorporated in the design process.
So are you asking, can we get to these?
It's on watching the videotape
Right.
with the analysis process. So that's a coupling
Yep.
of a sort of first order evaluation criteria. I'm just wondering if you have any thoughts about how you might be able to leverage concerns of these less immediately observable things, but nevertheless you want to impact
Yep.
your design iteration.
Yes, to the extent that any of those can be modeled, it would be nice to include modeling in the design tool, right? So I think Bonnie John has Cog tool, fantastic work at CMU, that allows you to take, if there are models that can predict human performance, then we should integrate those as well, yes. Now, do those models exist for some of the questions that we try to get at? I wish they did, because that would certainly hold the promise of making it much more rapid to get these answers rather than going through multiple iterations to a public deployment. Haven't found those yet. Yes. Thanks. Yes.
So you talked about sort of the artifact in gestation here is the design, or an implementation, a set of implementations of the design as a result of the process that you're supporting. Sort of the way I think of it, in parallel with that, there are things like customer requirements that may drive test criteria, for instance. Something either a relationship with the sponsor that sets some goals. So, in practice, it very often seems that the prototype of design evolves sort of hand in glove with the requirements, but there is the necessity of sometimes better efforts. The requirements do drive the direction in which the prototyping will proceed. Do you have a way of recording that, or is that out of scope with respect to this? And especially how you might keep the interaction with the customer alive and evolve it as prototyping evolves appropriately.
Yeah. So let me try to answer this. Well, step one is, I forget who that said, but who said the quote, but what's the difference between design and art? It's design happens for a client. Right? So you have someone else to answer to who you're not just creating it for yourself. So you're absolutely right that there is a set of constraints involved in that. And also, what you hinted at in your question is that even though these constraints exist, that problem setting and problem solving kind of go hand in hand during the act of prototyping.
And the consensus on those.
Yes. So for the work so far, as you said, that has been out of scope. I haven't looked at how to integrate that. I think it would be interesting to look at, because in a way, this was a thought I had this morning. In a way, integrating user test data into the design tool is similar in goal as very successful developer projects like Myelin, which integrate a bug tracking database into your development environment, right? It's always, there's some other domain of concern where you keep a list of things that have to be done, et cetera, and you want to integrate that into your production tool. So I think it's possible. What the exact solution would look like, I don't have a good intuition for yet.
Okay, thank you.
All right, thanks.
For more, please visit us at stanford.edu.